This proves that electric charge is a substance, aka lead. According to the solubility table, it is insoluble. So they lie again. We weighed the electric charge. Can you even imagine this?
Hello, dear friends. We welcome you to our podcast studio, and today he is our guest, Victor Tunov. Victor will once again share some interesting information with us. I hope he'll answer all the questions we've accumulated. Hello, Victor.
Hello, Alexander. Thank you for inviting me to your wonderful podcast studio, as is now tradition. Greetings, friends. Thank you for being with us, for watching, asking your questions, and showing interest not only in the power plant, but now in science as a whole.
That is precisely the fascinating subject we will be exploring and discussing, science, but we will delve much deeper into more intricate and specific questions. As
always.
Yes, we break everything down into details, everything step by step, little by little. I'd like to talk about batteries. As far as I understand the technology, the generation of energy and its subsequent delivery to the user doesn't happen directly. It's not like you generate it and immediately pass it on. There are also components where the energy is stored. These are the batteries. Could you tell us a bit more about this?
Of course, it is important to remember that the battery is also a separate, highly critical unit, and we will probably provide a very thorough general overview of batteries as well. Yes, we specifically use high-quality gel batteries here. And now here is a truly fascinating and interesting fact about these batteries that not many people actually know, Alexander, which might surprise you.
And
with this experiment, using a simple battery, Yuri Stepanov-Rybnikov demonstrated his findings. And this is yet another experiment through which he proved that the nature of electric charge is, in fact, a physical substance.
Yes, indeed.
Absolutely right. So in the experiment, we use a regular car battery. It's an acid battery, not a gel one, but specifically an acid battery, where sulfuric acid and distilled water are mixed in certain proportions and so on. As it turned out, if we continue within the framework of the experiment, it turned out that an electric charge has weight, and you can weigh it using a battery. Let me explain how. Watch. So we have a concept called electrolyte density. You know about that, right? A charged battery, a so-called charged battery, has a density of 1.28, right? And a discharged battery has 1.25 or 1.23, something like that. How? Discharged. So before charging the battery, the so-called charging, we're going to figure out what actually happens. So we take and drain the electrolyte from the battery, drain the electrolyte, and weigh it. We weigh it. It has a certain weight. Well, it will be different for everyone, right? Then we pour it back into the battery and connect it to the charger. In one of our podcasts, we mentioned that this is nothing more than a rectifier. We turn alternating current into direct current, and with direct current, we charge not the battery, but the electrolyte.
We fill it up.
We fill it with electric charges. What does this prove? And this proves that when a discharged electrolyte has a density of 1.23 to 1.25. I don't remember exactly anymore.
Let's be approximate.
If we're conducting an experiment, then we take it and charge it at 1 amp for 3 days. We charge the battery at 1 amp for 3 days. This is to ensure purity. Of course, at home, we charge it in a day, but for a clean experiment, we do it this way. We use 1 amp and charge it for 3 days. We set the density to 1.28, pour out the electrolyte, and weigh it. And the weight of the electrolyte increases by 10%. And we added current to it, direct electric current.
You might ask, how?
This proves that electric charge is a substance. Then they start telling us that a chemical reaction occurs and electricity is released because of that chemical reaction.
Yes.
If we look at the solubility table, they say lead dissolves. In general, everyone knows all this, I think, as they tell us how a battery works. But actually, it works a little differently, of course. Basically, if we look at the solubility table, plumbum, which is lead, according to the solubility table, is insoluble. So they're lying again. You see, they say there's a chemical reaction happening there. There is sulfation going on. Why? Because it's electroplating. But this electroplating of pure water, which is present there, of course, So what is done in a battery? A system of two types of lead is created in the battery. One is spongy lead, the other is non-spongy lead. We pass electric charges through them into the distilled water and acid. Distilled water is a dielectric. We together with you, amen. In one of the podcasts, we talked about how a dielectric accumulates charge on its surface. Do you remember? Yes, yeah. So without distilled water, you can't charge the acid. Only with distilled water, the electric charge dissolves, the weight of the electrolyte increases, and its volume increases. But everyone has seen that the volume increases. That's 100%. When recharging, you open up the cells, and check how much electrolyte there is. Well, you more or less notice it. It got charged and the level went up. The level. Where did all of it come from? You're only adding direct current from the mains. You're pumping it in, yes?
It couldn't have just appeared out of nowhere.
That's it, so draw your own conclusions, please. Let's get back to our system. We use gel batteries. Why gel batteries? Because they're safer. That's one. They're also resistant to damage. After all, we're transporting the power station. And if, for example, it's not secured properly and it falls over or something else happens to it, it'll still be safe.
Here, it's worth mentioning various types of seismic activity, meaning in areas where earthquakes are common. This is also relevant.
Absolutely right, yes. That's one of the important factors. Secondly, it's a gel battery. By the way, gelic is also a geoelectric, just so you know, for the record. And this battery, as of today, it has, at least as far as I know, it has the largest capacity, ampere hours, so-called ampere hours. It has 200. If we take, for example, a car battery, right? It has 75, maybe 90 ampere hours. I don't quite remember, but something like that.
But that's noticeably less.
Yes. And here we have 200 ampere hours. That's it. And in addition, we've set up a system. It's here in one of the cabinets, a system that produces 380 volts to start our compressor. We start up the power station even in places where, for example, there is no external power source. The simplest way, of course, is this. We bring the power station somewhere, there's electricity there, we connect the compressor, and that's it, right? It starts working? Yes. There's a second option. When our receiver is filled with air, we open it, generation starts, and the compressor kicks in. But if we don't have air here, and there's no external power source, then we have a battery.
Which gives the initial impulse.
A battery pack, yes, which starts the compressor. Well, with the help of the system that's been created, yes, we get 380 volts. Well, by the way, that's no secret either, it's not some special technology. For example, Tesla Mobile, they also get 380 volts there. The batteries, well, with a special system, they get 380. And the third use of these battery packs is in case of an emergency. If the power plant stops working, our much-suffering unit, the compressor suddenly fails, then the power plant, which is connected to your house, as we can see on the control panel, well, the power plant operates in emergency mode. There are two types of emergency modes. There's the emergency mode, so to speak, running at full throttle.
When everything is just
really bad. So, economy mode. I mean, the supply of electricity from battery systems. And everything will depend on the number of hours of operation. But in the emergency system, in the emergency state of the power plant, in other words, when the power plant is connected to your house, you get a stable and reliable output of 16 kilowatts, available 24/7. If we suddenly end up in an emergency, you can also get 16 kilowatts from the backup batteries. But keep in mind, this is only for a single day.
Because the storage capacity is limited.
Yes, you won't be able to get it for more than a day. At most, 16 kilowatts per day. But if we turn it on, a person can choose the mode. Well, I think in the future, we'll make it so that the person can choose whether they need it fully or not. 16 kilowatts, or it can operate in an economical mode. Then the system will supply electricity to the refrigerator.
To only the most essential things.
That's
rational.
Second day, the station can still operate and power the house. Our service team will arrive within...
Yes, I was just thinking about that.
To clarify, they'll fix the problem and that's it. We know exactly what broke and what needs to be done. And we can come and replace the component in the shortest possible time because our facilities will be located, as we mentioned earlier, already in India.
In points of close access so that the issue can be resolved as soon as possible. Yes, that's excellent.
We could also take into serious consideration, of course, the establishment of specialized service centers that could, so to speak, function and provide support under the broader framework of tribal technology. Some of them will be located in various cities, but I still think they won't be very extensively utilized or widespread. Why? Because this system is exceptionally dependable and robust regardless. And there's merely one single specific component that
requires attention.
And otherwise, for the most part, it's a very simple system that practically doesn't wear out. That's your battery, you see. Here it is. An extremely important discovery, further confirming that everything consists of electric charges. This is the battery. There you go. We've weighed the electric charge. Can you even imagine that? It's just not the volume, but the actual weight. Not at all. Of course, there you have both volume and weight and everything else. Can you imagine? It's just that simple. In the usual understanding, for most people, electric charge is the amount of time a gadget can last. Yes, I'll tell you, even more than that. An ordinary person has absolutely no idea what electric charge actually is. In our model, we have these very lithium batteries installed, and lithium, not gel. Oh, gel batteries. Sorry, I meant gel batteries, yes. There are literally just a few of them here. But as an ordinary person, I have a logical question right away. Why not 32? Why not 64? So if there's space, why not use more of them? Is there a specific reason for this, or is it just a limitation? Of course, there's a reason. First of all, it's not necessary, and you don't need 32 of them. 16 is enough. That's even with a margin. Plus, each one weighs 50 kilograms. So just do the math, take 16 and multiply by 50 kilograms. That's extra weight for transportation and so on. The lighter it is for us, the better. And what about the batteries? They also need to be secured and so on. These specific battery units themselves necessitate very specific and strictly controlled environmental conditions. As we have previously discussed in detail during one of our earlier episodes, there exists a complex and delicate internal ecosystem within them. It affects the batteries in the same way. Batteries need to be kept at a certain temperature. They have to be warm because when it's cold, so-called superconductivity appears. We've heard about that. Yes, superconductivity. But as Stepan said, there's nothing super about it. There's no real superconductivity. There's just maximum conductivity because atoms have their own conductivity limits. And when it's cold, well, here we should ask, what is temperature really? Where does it begin? But that's another story. If you want, we can talk about that too. Basically, when it's cold, everything contracts. And inside the atom, all the conductivity lines converge into one. And what you get is a continuous channel through which electric charges can flow. So we can say that as the temperature decreases, conductivity increases. Of course, they discharge faster. And that's why your phones lose charge faster in the cold, because what's called superconductivity appears. In fact, it's just complete conductivity. If any of our viewers are watching this podcast from a warm country and don't know what it's like, when your phone dies because of the cold weather, welcome to Russia. Come visit. We'd be happy to see you. It'll be a little experiment. Yes, we'll show you what superconductivity is. That's why batteries always need to be kept at a certain temperature. So this is definitely a plus, which is why every additional battery, since you mentioned there are 16, each additional battery will affect the internal ecosystem, all the necessary energy consumption, and the temperature that needs to be maintained. Each battery you're almost an engineer already, a technology trigger. You could work with us. Well, I think once we've covered all the relevant questions, I'll try to qualify for an engineering position. Maybe I'll have enough knowledge for that, which of course I don't have yet. And by the way, the batteries, they also get recharged here. The main generation comes from the main generator. From the 3B transformer, we receive the electrical power that is fully processed and ready for immediate use, which can then be distributed directly to the end consumers. Make sense? However, we first carefully direct this energy through our central hub. This hub efficiently distributes the electricity that goes to power the station itself and for the necessary charging processes. A. Kabe. And if there are 32 of them, as you can imagine, you need more. Yes, that is precisely the reason why our sophisticated system has been designed to include exactly as many as are needed for optimal performance. In fact, we even maintain a small strategic reserve of extra resources just in case of an emergency, much like the military does with their own supplies to ensure they are always prepared for any situation, you know. For all situations, yes, even electric janitors, those exist too. And there's always a hand that can, the system is duplicated, of course, that's a must. So if it's about autonomy, it has to be there, and reliability as well, and everything else too. And this system, this hub, it distributes electricity here and to the consumer. Yes. And this hub, it will never leave the power station without electricity. It won't let the consumer. So in my mind, I pictured it like this. The batteries are like a reservoir where energy flows in like water. And when the batteries are full, the excess overflows. And accordingly, the surplus goes outside and is then delivered to the user. Here, the system works differently. Here, it goes through the batteries. It passes through already, coming out of the battery further. And if it remains, yes, it's a bit different again, right? Look, our batteries are charged through the hub. The hub sends electricity to the batteries only when they are discharged. So if there's a shortage, the system will send it. But as soon as they're full, the door closes. That's it. It happens. That's how it is. You can't overcharge them. Well, you know you can't overcharge batteries. And for example, the well-known phones, the total charge, already those, the ones that don't
differ,
the ones that shut off so they don't overcharge, because that's harmful. An excessive electric charge is always harmful. So even if a person is in an excessive electric field, they can develop cancerous tumors and so on.
That is, all advanced technologies are very close to ordinary people, to regular citizens. Everything is very accessible.
Really, it's actually very simple. The simpler, the better.
Excellent.
So that is most likely everything you need to know regarding batteries.
There's one more small question. How, or rather not how, but in principle, is it possible for these batteries to somehow be integrated into a digital system to monitor their condition? For example, in case of some unusual reason or emergency situation, if one of the batteries fails, or if one of these 16 cells is not working properly, can their performance and operation be monitored using a digital system? Is that possible?
To carefully observe and track their performance levels, well, that is the main objective here. We can't monitor the performance of the battery. It's either working or not working. How can we monitor it? We just pour in the electrolyte. We don't have any system for that. So
there are only two states here.
Here, it's working. We can track the fact that it's working. And we can also track when it's not working. We can specifically monitor each of the 16 and label them and keep track, of course. But I think we've set up the system. In general, it exists. It's possible to implement it, but we haven't implemented it. If you're talking about this
at this very moment,
as I said before in one of our recent podcasts, and you should definitely take some time to go and check it out, listeners and friends, find it. We mentioned that the current internal system we are using right now is not actually electronic at all. Well, I mean, how should I put it?
It's not that there's no digital control.
This control, because, well, there's no digital software. You could write it, meaning it needs to be implemented there. That is, right now, everything we have is on paper.
We can say that this is a potential that is quite real. It's not some kind of technology that needs to be developed. It already exists. It just needs to be implemented.
It just needs to be implemented and connected. For one specific individual piece of computer software, it is absolutely essential that we utilize Microsoft.
So, as we discussed today, in the event of an emergency situation, the batteries will last from 1 to 3 days depending on the operating mode. And in case of a malfunction, a signal is sent, and this is already about digital monitoring of the station's operating status so that the specialist can come.
Of course, they'll come and simply replace 1 or 2, however many are needed, batteries. But as a rule, in my experience, nothing ever happens to them. That is, as much as I've dealt with gel batteries, on the contrary, they've only shown themselves from the best side. They perform excellently both in winter and in the heat. Even if, well, for example, this is a cabinet and this is a cabinet, they each have their own ecosystem inside. Actually, yes, because if something suddenly happens here, and after all, everything is here, the electronic control unit and so on, the cabinet has its own cooling or heating to ensure the cabinet survives and sends a signal.
So the whole system doesn't collapse at once.
But
Defense,
and the cabinet will always keep working. It will always report if something is wrong. In other words, the system will always show it. That's it. And these kinds of cabinets are used in cellular network base stations. And in such cabinets, when they're used in base stations, they have batteries installed inside them.
they are already separate, dedicated for...
This is the base station. So, if the primary main power supply is suddenly cut off, these backup batteries right here will immediately kick in to help. The base station consumes at least 1 kilowatt. At least. It can run for 3 days on battery power. And these same batteries provide electricity for cooling. There's an air conditioner there, or for heating. This same air conditioner just works in reverse, for heating instead of cooling. And if it can't work, or if it's really hot, for example, and it can't cool down fast enough, the batteries still work perfectly. If they start to freeze, they work perfectly. If they're in use, they kind of warm themselves up.
There's thermal regulation going on.
The distribution is more efficient. I think this is the best solution right now. Although, we were at an exhibition in Saudi Arabia, at the exhibition of alternative energy sources. We walked around there, yes, and by the way, we have a video. If you haven't seen it, you can check it out. And there were battery packs there, but they were unusual. They already had control systems. So, yes, they were like that. Right on the battery itself.
A digital module. Yes?
Yeah. So it already had some kind of radiator with cooling. So it was already more of a system like that. I picked up some materials there. I was looking for something so that we would have, fewer batteries to reduce the weight. Well, basically for safety, so that there wouldn't be so much electrolyte in there. Anyway, I keep looking. I think there are some innovations.
Maximum and complete modernization.
So that everything is as computerized as possible, so people can monitor and keep track of it. So there are already batteries like that. It seems to me there's still gel batteries. Helium is a dielectric. Here, the capacity depends exactly on that. If they come up with some other dielectric, not helium, then the capacity will be even greater. It's just that they've created some kind of interesting system there. And, it's mostly Chinese manufacturers. They were represented there. Maybe we could collaborate with them. There is
potential for development and modernization.
Absolutely.
Excellent. Victor, thank you very much for a very interesting and informative talk. Dear friends, we hope you found this episode interesting. Of course, we look forward to your questions in the comments. Write to us, ask your questions. It's possible that we'll create a full episode based on the questions you send us. Let me remind you, our guest today was Victor Tunov. Thank you very much for your attention. See you in the next episodes.
Thank you, Alexander, for inviting me to your wonderful studio. Friends, thank you for watching us. Be sure to write If you have any specific questions, please feel free to write them down in the comments section below. We truly make an effort to read everything and provide detailed answers to your questions. But I sincerely hope you found this presentation informative and helpful. Thank you very much for your kind attention today, and goodbye for now.